the big thing with inverses, I'm going to draw a picture, and then I would imagine that you've probably seen this picture before. Let me know if you can see all right. It looks like this. You have this circle and maybe this circle. This one represents your domain, and this one represents your range. And then basically there's some function that picks up a number here and does stuff to it and drops it out over there.
Mm-hmm.
So let's try that again. We'll call this f of x. So how I think about it is like, there's a lot of ways to think about domain and range and their relationship to the inverse, or the relationship to the function. Like an old way that you might have seen it when you were like in 4th grade, it's like, you have a number machine, and you put a number in, and it pops a number out, right? That's the same idea. That's the same thing that's going on here, is this f of x is your number machine, this is your input, and this is your output. So you pick up a number here, do whatever you do to it, and pop it out there. And each of these circles is just like a collection of numbers. Sometimes we're going to have limitations on numbers we can put in. We're, for the most part, typically going to have limitations on the numbers that can come out. So that's the general idea with a function. Have you guys talked about, I'd imagine, like horizontal line test, vertical line test? Yeah, so that this kind of stuff all plays into that. So kind of a simple concept that I like to do is talk about birds and birdhouses. So domains are your birds, ranges are your birdhouses. It's more just a conceptual thing, but we can have 2 birds that go to 1 birdhouse. That's totally physically possible. But we cannot have 1 bird trying to go to 2 birdhouses, right? Physically can't do that. So that's a way to remember about what makes a function, is that we can have 2 birds going to 1 birdhouse. That's fine. So visually what this looks like, let's put in a little, oh, there we go. We're live. So let's lock it. So let's say we have a parabola, and pick a color, or which one? Let's go purple. Here's our general parabola, right? So when we think about the horizontal or the vertical line test, we're testing to see if this thing is going to be intersected by vertical lines in more than one place. This one passes. The reason being is because in this point we have 2 birds, like 2 and -2, but they're going to be mapping to the same y value. But that's okay, because that's 2 birds just going to 1 birdhouse. Check. So the reason I'm spieling about this so much is because this is where inverses come in. So I'm going to draw that picture again, but now we're going to talk a little more specifically about inverses. So we come back here, I pick a number up, I drop it off there, I call that f of x. Now the catch is with inverses is it's only 1 bird to 1 birdhouse. The reason being is because what inverse does, and I'll change, we'll go to green for inverse. The inverse picks up a range number and brings it back to that original domain number.
Okay.
So the reason it has to be 1 to 1, I can't have 2 birds going to 1 birdhouse, because if I try to go backwards now, that's 1 bird trying to go to 2 birdhouses, which doesn't work. So the whole idea with inverses is this concept, 1 to 1. If you have 1 to 1, then you can have an inverse. How do we test for 1 to 1? Horizontal line test. So if I go into the horizontal line test here, it fails miserably, right? It fails a whole bunch of times. So like our parent function, which this is f of x equals x squared, no inverse, because it fails the horizontal line test. It's not 1 to 1.
Okay.
So functions that can pass might look, so functions that will pass are, say, like x cubed. So this is f of x equals x cubed, which is another one of the big parent functions. And so if I think 1, is this a function? Yes, it's a function that passes the vertical line test. I think 2, does it have an inverse? Yes, it passes the horizontal line test.
Okay.
So that stuff checks off. So the last concept here that really goes with inverses is that they have some cool symmetry stuff. Do you know what line they're symmetrical about? It's okay if we don't. It's a special one, but it looks like this, and I'm going to dash it in. It's symmetrical about the line y equals x. Or if you want to put that in like slope-intercept form, we could say 1x plus 0. So when they're symmetrical, it means that basically if I was to fold the paper on the line, the orange ink would like bleed or like print onto the other side. So it would look something like this. Its inverse would be here in the blue. Something like that. So to kind of recap, functions map from domain to range. Inverses map from range to domain. For it to be one-to-one, you have to have one unique x that maps to one unique y, so that when the inverse picks up that y, it maps it right back to that original x.
Okay.
They are symmetrical around the line y equals x, which we'll see a lot with exponentials and logs. That's a big thing there.
Okay.
I think that kind of covers it. Any general questions?